Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his master's in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series on B-architecture. In the previous lecture, we have seen the design of slabs, that is one-way slab, two-way simply supported slab, two-way restrained slab and one-way continuous slab. So, these are all the slab which has been designed based on the moment coefficients given in IS 456-2000, and we have found the bending moment and we have designed the thickness of the slab and the area of reinforcement required for the respective bending moment, and also we have seen in detail about the detailing of reinforcement based on SP 34/1987. In the present lecture, we are going to discuss about design of circular slabs. In this lecture, we are going to cover the design concept of simply supported circular slab. Normally, we all know that the simply supported circular slab means the slab which is supported at its end sleeve, whereas it is simply resting on the walls or supports. Next, it is fixed, both ends are fixed, that is the edges of the slabs are fixed, that is called as fixed circular slab. Then partially fixed circular slab and its behavior and the bending moment calculation and the reinforcement required for it. First, I am going to see the behavior of the slab, that is what is the bending moment for the 3 circular slabs and how to find out the bending moment for these 3 slabs. Before that, where the circular slabs are normally used? A roof of a room or hall circular in plan. If the room is a circular in plan, the slab has to be designed as a circular slab, that is simply supported or fixed circular slab. It is normally used in the circular water tanks or towers, and normally the roof of pump houses are constructed above the tube wells. So, here the circular slabs which plays a vital role. And we are also see the traffic control post, that is it is normally circular in shape. So, here the slab is designed as roof slab. So, these are all the various uses of the circular slab, the places where we are using the circular slabs. In the circular slab, how this circular slab which is behaved? In the circular slab, normally the bending which is taking place in 2 perpendicular direction. So, the reinforcement should be provided along both the direction, that should be in the form of mesh reinforcement, since it bends along both the direction. In some cases, in the case of simply supported slab, there is a radial bending moment as well as the circumferential bending moment which is developed. Among these 2 bending moment, we need to select the maximum bending moment, and for the maximum bending moment, we need to provide the reinforcement along both the direction, that is radial, that is along both the direction in the form of mesh reinforcement. Sometimes in the case of circular slab, there is a circumferential moment which is normally developed at the ends of the slab. There is a circumferential moment and the reinforcement which is required for the circumferential moment which is normally placed at the bottom, that is over the mesh arrangement of reinforcement around the edge of the slab. That reinforcement which helps to avoid the sliding of reinforcement at the edges. It is also provide an anchorage to the mesh form of reinforcement at the edges. This has to be provided over a development length of the reinforcement. So, this is to avoid slippage or sliding of reinforcement at the edges. This is the circumferential reinforcement at the edge of the slab. But in the case of fixed slab, the fixed slab, there is a bending moment which is occurs at the edges, that is a radial bending moment, there is a negative bending moment. that to resist that negative bending moment, we need to provide the reinforcement at the top in the radial direction. So, in order to keep that radial direction moment or radial direction reinforcement, that has to be uniformly spaced, and in order to distribute that radial reinforcement at the top for up to a distance of point of contraflexure, the reinforcement has to be tied up with a circumferential reinforcement. That reinforcement which is mainly used to distribute that reinforcement at the top with a proper spacing, and also it is also used to avoid that sliding of reinforcement from its respective places. And here in the case of bottom reinforcement, at the edges we need to also provide a circumferential reinforcement for over a length of a development length of the reinforcement. That much amount of circumferential reinforcement which is also used to avoid the sliding of reinforcement at the edges, and also used to keep the reinforcement with the proper position. So, here this is the behavior of circular slab. In the circular slab, we must also consider what are the load which is uniformly distributed over the entire area of the slab. So, the load which are normally due to dead loads and live load, we are going to find out what are the dead load. Dead load normally includes self weight of the structure itself and the weight of floor finish, and in addition to this dead load, we need to also consider dead load, live load. So, we are going to find out total load which is acting on the slab. Using the total load, and also we know the radius of the slab, we are going to find out the radial bending moment as well as the circumferential bending moment. The radial bending moment which is denoted by mr, and the circumferential bending moment which is denoted by m theta. There is a radial bending moment at the center, and there is a radial bending moment at the edge. The radial bending moment at the center, it is called as mrc, and radial bending moment which is at the edge is mre. And there will be the circumferential moment which is at the center as well as at the edges, that is denoted by m theta c and m theta e respectively. Now, we are going to see the behavior of simply supported slab which is subjected to UDL, and how to find out the bending moment, and how to provide the reinforcement in the case of simply supported slab, circular slab with a UDL. So, here I am going to draw the circular slab. This is a circular slab. So, here which is simply supported at the edges. This is the circular slab. So, here when you take this section, when you take this is the circular slab which is simply supported at the ends. So, here the radius of the slab is taken as A, which is subjected to some kind of uniformly distributed load. This is W kilonewton per meter square. Where the bending moment, where the maximum bending moment, where the radial bend, what is the radial bending moment as well as what is the circumferential bending moment. So, here then how to provide the reinforcement in this case. So, here this is the radial bending moment diagram, circumferential bending moment diagram. It is denoted by m theta diagram, that is circumferential moment diagram. There is a circumferential moment at the center, that is 3 by 16 W A square, and there is a circumferential moment at the edge, it is 2 by 16 W U A square. This is a circumferential moment diagram for a simply supported slab. So, to resist this circumferential moment at the edge, we need to provide the reinforcement at the edges over a distance of the development length of the reinforcement in the circumferential direction, that is around the edge of the slab. Next, the radial moment, since it's simply supported circular slab, the radial moment at the edge is 0, and the maximum moment which is normally developed at the center, at this moment is 3 by 16 W A square, which is equal to the circumferential moment at the center. Well, how to design the simply supported slab, thickness of the slab as well as area of reinforcement required for it. So, here we are having two moments, one is circumferential moment, another one is the radial moment. So, here the moment, circumferential moment and the radial moment at the centers are almost equal, that is 3 by 16 W A squared. So, from the moment we are going to provide the reinforcement at the bottom, both are positive, this is here positive, this one is positive. So, we need to place the reinforcement at the bottom, that is now reinforcement details. Now, here this is the circular slab. In order to resist this moment, the reinforcement should be placed along both the direction. So, this is the reinforcement should be spaced along both the direction in order to resist the bending moment, that is 3 by 16 W A square. This is the reinforcement at the bottom. This is for resisting m theta at the center and m r at the center. This is a form of arrangement of reinforcement to resist the bending moment. Now, in order to resist the bending moment, that is at the support, that is near the support, that is 2 by 16 W A square, that is circumferential moment reinforcement, the reinforcement has to be placed in the circumferential direction. This is the moment reinforcement and this is the circumferential moment reinforcement. At what distance the reinforcement has to be provided? This is the moment has to be provided for a distance of LD from the face of the support. The development length of reinforcement is pi into sigma st divided by 4 tau BD. This is as per IS 4/6. So, to resist this bending moment in the case of simply supported circular slab, the reinforcement has to be provided at the bottom for resisting the radial as well as the circumferential moment at the center as well as the circumferential moment at the edge of the slab. So, this circumferential moment at the edge of the slab, that is in the circular form, which is used to resist the sliding of this mesh form of reinforcement at the edge. It is also provide necessary anchorage to this radial moment reinforcement at the edges. Normally, there is a chance of slipping up of reinforcement at the edge. In order to keep this reinforcement in the proper position, the reinforcement has to be provided. It is also not only to resist the circumferential moment at the edge, it is also to keep the main reinforcement at this respective place in order to avoid the sliding of reinforcement. This is in connection with the simply supported circular slab. Next one. So, here that is the thing, circumferential moment at the center of the slab is 3 by 16 W A squared and circumferential moment at the edge of the slab is 2 by 16 W A squared. The circumferential moment at any distance r from the center of the slab is m theta W is 16 d A squared minus r squared. The radial moment at the center of the slab is 3 by 16 W A squared and the radial moment at the edge is normally 0. And the radial shear force, which is normally F r equal to 1 by 2 W r per unit width. Note that the circumferential shear force is 0 at everywhere. Next, we come to the fixed supported circular slab with UDL. Now, this is a circular slab which is fixed supported at the edges. Now, the radius of the slab is A. Now, here when you draw the cross section, this is the cross section of the slab and this is fixed supported at the end when it is subjected to some kind of forces, that is W kilonewton per meter square. Now, what is the radial as well as the circumferential moment? So, here the circumferential moment at the edge of the slab is 0 and the circumferential moment at the center of the slab is W A squared by 16. This is M theta diagram. And this one is, since it is fixed slab, there is a moment at the edges. The moment at the edge of the slab is, this is the deflection nature of this. Normally at the edge, the slab will be deflected in the fixed end. Now, here it is 2 by 16 W A square, this is minus, and this one is positive, this is W A squared by 16. So, here the distance of point of 0 bending moment from the center of the slab is A by root 3. So, here also it is denoted by A by root 3. And how to provide the reinforcement to resist this moment? So, here this is the circumferential moment, this is MR diagram, that is radial moment diagram. So, here first to resist this radial as well as the circumferential moment at the center, the reinforcement has to be provided along both the direction in the form of mesh at the bottom. This is the reinforcement at the bottom. Is correct. Now, here in the case of fixed slab, since it is fixed, there is a radial negative bending moment at the support. So, in order to resist this radial moment of 2 by 16 W A square, we need to also provide the reinforcement at the top. This is the figure, shows the top reinforcement. This is in terms of, this is along the radial direction. At what distance the reinforcement has also to be provided, that is most important. That is for a distance A minus A by root 2, the distance of length of this reinforcement, because the point of contraflexure which is occurs on either side of the center of the support, center of the slab is A by root 3, and the remaining distance we need to provide the reinforcement, that is A minus this area radius of the slab is A minus A by root 3 is the remaining distance. Up to the remaining distance, the A by root 3, the reinforcement has to be provided. This is the top reinforcement, and in order to keep this reinforcement at the top in a radial direction, we need to provide the reinforcement in the circumferential direction, that is called the circumferential moment, that is called as a minimum reinforcement. That minimum reinforcement which is used to keep the top reinforcement with the proper position, or which is also used to avoid the sliding of reinforcement at the top, that is a circumference. Minimum reinforcement has to be provided. And the radial moment, which is radial moment, the reinforcement, it is from the moment of 2 by 16 W A square. So, when you take the cross section of the slab which shows the reinforcement, this is fixed supported, and the bottom reinforcement, that is we are providing along both the direction, that is in the form of mesh. So, this is the radial reinforcement, that is radial moment or circumferential moment at the center, and this is the top reinforcement, this is the length of reinforcement, that is the radial reinforcement, and this is the circumferential reinforcement. So, here this is the reinforcement which has to be provided from the face of the support A minus A by root 3. So, this is the arrangement of reinforcement in the case of the slab which is fixed at the edges. Next, as another slab which is called as partially fixed slab. This is the fixed slab, another one is the partial fixed slab. How to find out? This is the partial fixed slab. So, here this is a symbol of simply supported. When you take the another direction, it indicates the fixed or partial. So, here the radius of the slab is A. Now, we need to know we need to draw the cross section. Now, this is the fixed slab, partial fixed slab. The radius of the slab is A. Now, to find out the bending moment. So, here in the case of partial fixed slab, there is a circumferential moment there at the edge as well as at the center, that is m theta diagram. Circumferential moment. So, here at the center is 2 by 16 W A square, at the edge is 1 by 16 W A square. Since it is a fixed slab, there is a negative radial moment which is developed. Anyway, it is partial fixed slab. The moment here it is minus 1 by 16 W A square at the edge, that is W A square, this is a negative moment. At the center, it is 2 by 16 W A square. This is a radial moment diagram for this. And how to resist this radial moment as well as the circumferential moment by means of reinforcement. So, this is the plan of the slab which shows the bottom reinforcement. So, to resist the circumferential moment at the center and the radial moment at the center, the reinforcement has to be provided along both the direction. This is the positive moment reinforcement at the center, that is the bottom reinforcement. And in order to resist this negative moment at the edge, that is a radial moment, as well as the circumferential moment, there is a reinforcement which has to be provided at the top. So, this moment, the point of contraflexure which occurs at a distance of A into root 2 by 3. This point of contraflexure on either side of the center of the slab which occurs at a distance A into root 2 by 3. So, here for the remaining distance, the reinforcement has to be provided, that is A minus A into root 2 by 3. For that distance, that at the top the reinforcement has to be provided in the radial direction, which is used to resist the negative radial moment at the support or at the edge, that is 1 by 16 W A square. The length of this reinforcement is A minus A into root 3 by 2 up to the point of contact. Normally, the reinforcement not supposed to stop at the point of contact, it has to be extended beyond the face of the support for a distance equal to effective depth of the slab. But as far as the diagram is concerned, the reinforcement at least has to be provided for a distance of A minus A into root 2 by 3. And in order to keep this reinforcement with the proper position and also to satisfy the circumferential moment of 1 by 60 W A squared, there is a circumferential moment reinforcement which has to be provided in the circumferential direction. This is the reinforcement which is not only to resist this circumferential moment, which is also to keep the top radial moment reinforcement with the proper position and also to avoid the sliding of reinforcement. So, here when you take the cross section of the slab, so here this is the cross section of the slab, this is partially fixed at the ends and this is the radial moment reinforcement at the bottom, that is in along both the direction of the slab. And in order to resist the radial moment at the top, since it is fixed, there is a negative moment at the top. This is for a distance of A minus A into root 2 by 3 on both the ends at the top. In order to keep this reinforcement and also to resist the circumferential moment at the edge 1 by 16 W A squared by 2, so W A squared, the reinforcement has to be provided in the circumferential direction. So, that is called a circumferential moment reinforcement at the edge. This is the arrangement of reinforcement. So, before designing those slab, first we must know what is the behavior of the slab, how to provide the reinforcement required for that, we must know it. So as far as the civil engineers and the architectures are concerned, so we need to, while we checking the reinforcement at the field, we must know the detailing of reinforcement before entering into the field. That is most important. So this is the arrangement. So when you go to the place where the circular slab is casting, so we must know the arrangement of reinforcement. And while we study this one, when you before going into the site, this is very easy to check the reinforcement detailing by referring with the reinforcement drawing. So this is the behavior as well as the arrangement of reinforcement for simply supported and partially fixed and fixed circular slab. So here in the case of partial fixed circular slab, the circumferential moment at the center of the slab is 2 by 16 WA squared, at the edge of the slab is 1 by 16 WA squared, and radial moment at the center of the slab is 2 by 16 WA squared, and at the edge it is 1 by 16 WA squared, and the radial moment at the point of contact fluxure which occurs at A into root 2 by 3 from the center of the slab, A into root 3 by 2. With this we have learned about the circular slab and the places where the circular slab is used, and also the behavior of the slab, and also the reinforcement detailing. Let us summarize this lecture. In this lecture we have seen in detail about the behavior of circular slab, that is simply supported circular slab, fixed circular slab, and partially fixed circular slab, and also where the slab which is normally used in this circular slab, the places where we are using the circular slab, and also we have seen in detail about the bending moment diagram based on its behavior of the slab, and based on the bending moment where we have to provide the reinforcement and how the reinforcement has to be provided in the case of these 3 slabs. That is we have seen in detail. And in connection with this lecture, the questions may be arised. Give the uses of circular slabs. Explain the behavior of simply supported circular slab with moment diagram. We need to know how to explain the behavior of simply supported slab with the moment diagram. Explain the behavior of fixed circular slab with moment diagram. Explain the behavior of partially fixed circular slab with the moment diagram. And then draw the reinforcement detailing of above said slabs. That is, we need to know the detailing of reinforcement for these 3 slabs, that is simply supported circular slab and partial fixed circular slab and fixed circular slab. In connection with this lecture, the references are IS 456-2000 Plain and Reinforced Concrete Code of Practice, IS 875-1987 Code of Practice for Design Loads other than earthquake for buildings and structures. Normally we are considering the vertical load which is acting on the slab as far as our condition. We need to also consider, first we must know how to design the slabs subjected to vertical load. We can also consider the earthquake forces along with the vertical loads. So in our syllabus we are having only the subject, that is the slabs which is subjected to the vertical loads. The vertical loads here we are considering is dead loads and live load. And we must know the detailing of reinforcement required for the circular slab by referring SP 34/1987. And also the books. So there are 2 books, that is the well known books, that is written by S. N. Sinha. The title of the book is Reinforced Concrete Design, which was published by Tata McGraw-Hill Publishing Company Limited, New Delhi. There is a new editions also arrived. Next, the Ashok K. Jain, that is the Reinforced Concrete Limit State Design, which is published by Nemchen and Brush, Roorkee Design. These are all the certain references we can make for the design of the circular slab. So the IS codes are most important. Normally we must follow the IS codal provision to design the slab, and also we can refer certain books. So without books we can't design the slab, but we based on the behavior of any structure we can start designing. The behavior of the slab we must know it, any structure or any element. So by referring these references we can start designing the slabs. With this we can finish. So thank you very much.